All right, welcome. So today we're going to talk about differential equations. We talked a little bit about them when we started talking about slope fields, but we're going to define them a little bit better today. And then talk about what does it mean to be a solution to a differential equation, okay? So let's start with the definition, a differential equation. So I think I just sort of said out loud what that's the definition was to a differential equation was last time, but we're going to write it down this time. So a differential equation is an equation that contains an unknown function and one or more of its derivatives. So an equation that contains an unknown function and one or more of its derivatives. So we have been actually, differential, that comes from the word differentiate. So when we differentiate, we find the derivative. So a differential equation really describes what it is, which is like an equation involving derivatives. And so we have been actually seeing these a lot because, like, here's an example of a differential equation. Y prime equals x cubed. So that's a differential equation because it involves the derivative of y, and y being the unknown function. In this particular case, finding y, or at least the function of families, that is y, is not very difficult. We just take the antiderivative. So what we're going to get into, though, are examples that are a little bit like fancier and trickier. We're going to have things that pop up, and you've actually seen them. They've popped up on tests before. Things like p prime equals k times p, where k is a constant. In this case, the derivative of p is defined exactly with p, not another variable there. So that's interesting. So we'll see that pop up sometimes. There are other ones. There are like y prime equals ky times 1 minus y over 2. So there y pops up a couple of times. These are actually like forms of pretty famous differential equations, so we'll see these maybe pop back up later on in life here. Another one is if you've like taken physics here, we have so x double prime equals negative k over m times x. This has to do with sort of like springs, and this is called a second order differential equation because it involves the second derivative there. And if we're talking about the second derivative of x, which is probably a position, we're probably talking about acceleration here. So anyways, so we'll just finish it off. Y prime equals xy. So x being sort of this independent variable, but y being a dependent function, an unknown function. So note that this is like another way you could write this is f prime of x equals x times f of x. Here I think this version sort of shows you very clearly, oh yeah, like we're dealing with some unknown function f, and that derivative of f is dependent upon the function f. So let's go ahead and get into sort of seeing what it means to be a solution. So just a quick sort of reminder, when you're thinking algebraically, like is something a solution, the way you check to see if something is a solution is you just plug it in and simplify to get a true statement. So if you think back to Algebra 1, you solve equations, or Algebra 2, pre-calculus, you solve equations, you get, cool, the square root of 6 is my solution. Well, if you plug in square root of 6 to the original equation given to you, you should get a true statements like 0 equals 0, 14 equals 14, x equals x, things that are just like obviously true. Identities is what we call them. So that's sort of the same idea here. If we want to find a solution to a differential equation, we're trying to find things that we can plug in for f and f prime and show that we get the same expression on both sides. So if we knew what f was, well then we could find f prime, plug those in, do some quick simplifying, and then voila, we got it. So let's see how this goes for us, okay? So we're going to take a look at this example. We want to show that every member of the function family y equals 1 plus c e to the t over 1 minus c e to the t is a solution of the differential equation y prime equals 1/2 times the quantity y squared minus 1. So it says that it's a family of functions because c is some constant here. C could be any number, and according to this, it doesn't matter what c is, it should work when you plug it into this differential equation. So we want to plug in and show that we get the same thing on both sides. The first thing to plug in is pretty obvious. Y is this expression. So for y here, we're going to substitute that in. But y prime is less obvious because we still have to find that. So that's going to be my first goal, is I'm going to find y prime. Okay? So to find the derivative of that, I'm going to use the quotient rule. So derivative of the top is going to be c e to the t times the denominator. Now the derivative of the denominator is negative c e to the t. I can see some nice stuff is probably going to happen up here, some good adding to 0, and then times the the top, sorry, c e to the t. And that is all over the denominator squared. Okay, so let's simplify this before we move forward here. So I'm going to go ahead and distribute. So we got c e to the t minus c times c is c squared. E to the t times e to the t is e to the t squared, or e to the 2t. And then now I'm going to distribute this, so since it's negative, it's actually going to end up being distributing a positive c e to the t, so it's positive c e to the t, and then positive c squared e to the 2t, all over 1 minus c e to the t squared. Okay, and so now I recognize that these two terms will add to 0. Those are like terms, so I can add them together. So I get 2ce to the t all over 1 minus ce to the t quantity squared. Great. So now I can substitute that in for y prime. So I'm going to go ahead and do this. So I want to rewrite this. Y prime, so instead of y prime, we're going to go 2ce to the t over 1 minus ce to the t squared equals 1/2 times y squared. So y is this original function family here, 1 plus ce to the t over 1 minus ce to the t. I'm going to square that though, because it's y squared, minus 1. Okay, so this left side is already fully simplified. We already did all that work up here. So what my goal here is to restructure the right side until it matches the left side. This is sort of like, thinking back to your trig identity sort of proofs. Usually I got one side that is fairly simplified and you're just trying to maneuver the other side. So that's what we're going to do. We're going to maneuver this side until it looks like this. So the first thing I'll have to do here looks like is I'm going to have to expand this thing here. Okay. So let's do that. 1/2 times, and this is going to be 1 plus 2ce to the t plus c squared e to the 2t all over, and you can check that that math if you wanted to, like an area model might help you out there, you know, do the little box, but that works out. And then here we got 1, and then it'll be minus 2ce to the t plus c squared e to the 2t. So I've expanded that out, I've squared that, and then what I notice is I'm going to have to subtract 1 from it. And since I don't want to, I want to combine those two things, I don't want two terms here, I'm going to go ahead and write a fancy looking one. So minus fancy looking one, common denominator is what I'm going for here. So minus 1 minus 2ce to the t plus c squared e to the 2t all over the exact same thing, because we want it to be equivalent to 1. Okay, so what do we get here? So 1/2 times, all right, so we're going to subtract the numerator here, 1 minus 1, bye-bye. 2c to the t minus a negative 2ce to the t. Oh, that's going to be 4ce to the t. C squared minus e to the 2 minus c squared, oh cool, that goes to 0 as well. So leaving us with 1 minus 2ce to the t plus c squared e to the 2t. And now at this point, I've got multiplication. So if we multiply straight across, we'll all have a 4 divided by 2. So that's going to leave me with 2ce to the t over, and well, this denominator here, I got that by squaring this. So I'm just going to rewrite it back that way because it makes it super clear that now the denominators match up with each other too. So I've got 2ce to the t all over 1 minus ce to the t quantity squared, and that verifies it. This function family is a solution for this differential equation. So to recap, essentially what you're going to do is you're going to be given a function family. You're going to probably need to find its derivative, or maybe a second derivative, and you're going to plug it in and verify that the left and right hand side are in fact equivalent to each other. You really want to take it down to this. Be super obvious. If there's still several steps left over and you haven't shown that you have exactly the same expression, you haven't quite shown it yet, because you haven't proven to the reader. That's the whole idea. Prove to the reader. Assume that the reader needs everything spelled out for them, okay? So this is what we'll be doing here in class today, is verifying these things. Please take the survey after this, so ask me a question and get your single point. Thank you.